Why
That's
not?
what these things are for.
Probably not going to sleep anyway.
Yeah, I am.
Okay.
Not if I put.
I didn't get the lesson. So I could go.
Yes.
No,
Steven's
none of us
hoarding
did.
all the
I'm
lessons.
the only guy.
Whoa. You know what? Let me come to you guys today.
Prom day, for God's sake.
Deliver with a smile. Yeah. Okay, so today we're talking about. There you go. Today we're talking about cells. Now, not those boring biology cells that
Who
are
cares about
the
those?
foundation of all life.
Voltaic cells.
The much more interesting voltaic cell. Yeah. Specifically, today we're talking about galvanic cells. Now, what is a cell?
Something.
Something that can storing.
Something that does
Produce power.
Yeah. So, long story short, it is a way to use chemical energy to produce electrical energy. So, what kind of reaction is that going to be? What kind of reactions have we been doing hypothetically, say, this whole unit?
Oh, redox.
Hey, there we go. Yeah, it's a redox reaction. It's a reduction and oxidation reaction. Remember that these happen in pairs. One thing is reduced while something else is oxidized.
Oh,
Good.
so it's like a battery.
It is a battery, yeah.
Jeez.
A battery is a battery of cells. Battery meaning there's a bunch of them, cells, I mean, what we're talking about today.
I just thought
In
the
each
copper
battery,
was
Yeah.
Oh,
So, in this case, the first example we're going to look at is the redox reaction between copper and zinc. Now, I picked a nice simple example, and for this whole lesson, we're going to stick with mostly simple examples. And then the last example is like marginally difficult, and I already screwed it up once today, so I think I'll try and get it right today, for this period. But if I wanted to break this down to its half reactions, zinc and copper, what would the two half reactions be?
solid.
Okay, so Zn sol. Oh, I don't want red. That's better. So zinc solid. Okay, now if we were going to, of course, make this a balanced redox reaction, I have the right number of zincs, so I don't need to worry about that. What's the next step? Electrons. Which side needs electrons?
Right.
How many? Good, very good. And then I would add H pluses to balance charge. Do I need any? Then I would add waters to balance oxygen. Do I need any of those? No, so we're good, yeah? Looks good to me. So there's one of our two half reactions. What would the next half reaction be? Yeah, does it have a charge?
+2.
Yep.
+2E negative.
Good.
Goes to copper salt.
Very good. All right, there we have the second half reaction. Now this is not new, correct? This is what we've been doing. And in fact, these are nice, easy ones. There you go, ladies.
Thank you.
So, looking at this, which of these is reduced? Top or the bottom, which one is reduced? And which one is oxidized?
Obviously, it has to be.
Good, that's true.
Obviously, like, well, there's not more than one reaction going on here.
He's right. Okay, so now the question becomes this. And I know you could just look at the diagram, but let's talk our way through this. The challenge with a battery, and I mean a battery just means a bunch of cells put into one container. But the problem with a voltaic cell of trying to take a chemical reaction like this and harness the energy is that if I just put solid zinc with copper ions, and I could use, say, copper sulfate, right? If I use CuSO4, that would give me Cu2 plus ions. If I put those two things together, what's going to happen? Sure, they'll react and they'll go to completion, right?
Oh, yeah.
Now, even though electricity will have been involved, can I harness that electricity if I just put them in one container together?
No.
No, the electricity is used to complete the reaction. And it'd be an exothermic reaction, and that energy would end up, when all is said and done, being released as heat. I'm not gaining any of it. I suppose I could build some device to capture the heat. Yes. So now, you want respirators, I hope. Right? I gave her drugs, now she's giving me money. That's the first. First you give the person the drugs, and listen, if somebody ever tries to tell you like money first, you say no. No, that's not how this works, right?
You get that?
Yeah, exactly. You saw how this went. There you go. It's for the athletic banquet stuff. Yeah, no. Drugs. Hi, Miss Burns. 2 weeks, ladies and gentlemen. 2 weeks left. Just gotta stay employed. No, that's crying in baseball. Okay, so if we just mix the things all together in one container, mix them all together in one. Anyway. It's called A League of Their Own. Tom Hanks and there's no crying in baseball. Anyway, so the challenge is, can we set this reaction up in a way where we can do two things? A, we want to harness the energy. We want to be able to collect the electrical energy, right? By the way, looking at this, what is the carrier for electrical energy? Electrons. Electrons carry that electrical energy. So we want to design a cell in such a way that we can harness those electrons. The second thing we need to do is, do we want the reaction simply to happen all at once and release all its energy and be done?
No.
No, that would be a very ineffective battery, right? We think of a cell as something we use to store energy and then use it to do work, right? So we also need to make sure that the reaction only happens when we complete that circuit, right? So here's the challenge. We need to have zinc ready and waiting to become zinc 2+. And we need to have copper 2+ ready and waiting to become solid copper. The solution is what we call a cell. And this is a wet cell. And it's sometimes called a voltaic cell. You'll see it called a galvanic cell. But how it works is this. On the left side, we have zinc metal. Because what is the first half reaction here? Solid zinc becomes aqueous zinc. So if you look, we have a zinc anode here, and it is solid zinc. And as the reaction happens, it is becoming zinc 2+ ions, and those are finding sulfate ions, SO4 ions, which we have made available so that the charge stays balanced, okay? Because it's important the charge stays balanced. Why? For a few reasons. One, because if we had a positive charge building up, Le Chatelier's principle tells us that that would actually drive the equilibrium in the wrong direction, and it would prevent the reaction from going to completion. So if we let those Zn2+ ions just build up and up and up and up, that's going to build up the things on the right side of the equation, which is going to mean that Le Chatelier's principle is going to drive it back to the left, which is exactly what we don't want. Does that make sense? So we need to provide those SO4- ions to charge balance to allow the reaction to continue. Does that make sense? As this happens, what's going to happen to that zinc plate? Yeah, it should be getting smaller.
Is that why a battery dies?
Yeah.
Holy shit.
So it gets smaller. As the reaction occurs, this zinc plate is being used up. And again, is that an oxidation reaction or is that a reduction reaction?
Oxidation.
Yeah, because it's giving up electrons. Now, where do the electrons go? Yeah, we have separated the zinc from the copper. But the electrons have to get from the zinc to the copper. So we run a wire between the two. And in the middle of the wire, we put
A source.
a source.
Energy.
No, I'm just jumping because I'm trying not to fall asleep.
A light bulb.
I mean, in this case, a light bulb, a load. Sometimes we call it a sink. Yeah, not a source, but a sink. But yeah, we put the place where the energy is going. Have you never heard that
Energy sink.
energy sinks? Anyway, we put the load. We put the place so the electrons leave the zinc with some energy, and the electrons are going to end up in the copper. The electrons are going to end up in the copper, but the nice thing is before they get to the copper, we can put something there that steals all of that energy. And we can use that energy to do something else. Yeah.
What makes the electrons go up the wire? Why do they want to go?
Because they want to complete the reaction. So we've always thought of a reaction as happening because we put the two things next to each other and they collide.
Yeah.
But that's not what drives redox reactions. Redox reactions aren't driven by collisions. They're driven by electrical potential. They're driven by the natural desire of electrons to leave a less electronegative thing for a more electronegative thing. Yeah.
In the picture, the wire between it looks copper. Would it be copper in real life, or would they use something?
You could use copper. Now, the part of that copper wire that's in the solution will then start to get bulked up just like the copper plate does, and that's true. You would find that if we made one in lab and you did use copper, you would have that problem. I mean, it's not really a problem per se, but that you will have that effect. It will behave in exactly the same way as the rest of the copper was. And I imagine that probably in an industrial setting, they would gold plate it or plate it with something else that was very non-reactive to prevent that happening. Though I don't know. That's an assumption on my part. Now, on the right side, we have a copper plate, but the copper plate isn't what's involved in this reaction, is it? Because what's the second half reaction?
Aqueous copper goes to solid.
Aqueous copper. So when the electrons get to the copper plate, they come into the copper plate just because it's a conductor, right? Conductor can carry electrons. But once they're on that copper plate, the electrons want to jump to aqueous copper ions, because that's where the reaction is going to end. And where are they?
In the water.
In the solution. We've used copper sulfate in this case. So the copper 2+ ions will get those electrons off the copper plate. And when they do, they will become solid copper, and they'll be deposited onto the plate.
Or onto the rest of the cell.
Sorry?
Or onto the rest of the cell, like on the sides.
Could be, but just by virtue of where they are getting the electrons are on the plate, so they're already right there. So the effect is almost always, not almost, it is always, that this plate is going to get plated. Now, if you had current building up on the walls, then sure, it could also be plated. But this is, by the way, this is how we make batteries. It's also how we electroplate things, you know? So when you buy something, you know, even say pennies. Pennies are made of zinc, but then they're electroplated with copper.
Oh.
Yeah, pennies, not copper. Pennies, almost like 96% mass, zinc, because it's cheaper. But because we expect our pennies to be copper, they then electroplate them in copper. A whole process that was very expensive and made them much more expensive than 1 cent to produce each, and that's why we don't use them anymore.
I also did that with jewelry.
Did you ever see, this was, Mr. Vanderberg showed me this lab, and I wish I'd known about it, where he cut the bottom off a penny and left it sitting in acid, and the acid will react with the zinc, but not with the copper, and you end up with a perfect hollow shell of a penny. Yeah, I can't wait till next time I teach grade 10 when we do like single displacement reactions. Pretty cool stuff, yeah.
We're dying. Nickel.
No idea. Probably also nickel.
Actually, steel's expensive, so you
Yeah, I doubt it would be. I would be surprised if it were iron.
So can we do this?
Yes, we're gonna. That's gonna be our last act of the year. Now, as this reaction happens, what's gonna happen to the copper plate? Yeah, it should get bigger. And again, that's because the copper ions from the solution are becoming solid copper and depositing themselves onto the plate. Now, again, it's important that charge be balanced. It's important that charge be balanced. So as those electrons are coming in and making the whole solution more negative, it has to get rid of some negative ions. So the left side needs to be gaining negative ions all the time to make the charge balance, right? And the right side needs to be giving them up all the time so that the charge balances. Does that make sense? And so we separate them, not with a firm, hard wall, but we actually separate them with a wall made of a salt, made of something with sulfate, typically sodium sulfate in this case. Does that make sense? So we separate them. Actually, pardon me, no, it wouldn't be sodium sulfate, I'm lying. It would be something insoluble. I'm not sure off the top of my head. I should know that. I should look that up. I will. But anyway, we use a salt bridge between the two so that it will allow sulfate ions to deposit on one side and remove from the other. Does that make sense? So this allows a constant flow of negative sulfate ions from this side where they're no longer needed to balance charge to this side where they now are needed to balance charge. And that's the setup of a cell. So it controls the flow of electrons because electrons can't flow through this wall. The only way they can get around to make the reaction happen is through this wire that we set up. And then if we want the reaction to stop happening, what do? Yeah, we disconnect the wires and the reaction stops. And it's left in stasis.
So how does like a rechargeable battery work?
We'll talk. We'll get there.
It gives back zinc.
I mean, you're literally just reversing the reaction. You put energy in, which Le Chatelier's principle tells us is going to drive the reaction in the other direction, and it does. Now, there's some caveats to that of it has to be set up a certain way, and certain chemicals will work for that and some won't. But now, it helps to name these plates. So we name this plate on the left the zinc, and the zinc was being what again? Oxidized or reduced? Oxidized. We name that the anode. And on the right side, the side that is being reduced, the plate that is being built up, ironically enough, reduced, is called the cathode. Yes.
It's a potassium.
Potassium. There we go. Now, there's a little mnemonic device for remembering which is which. I really hate this mnemonic device. I think it's stupid, but I'm going to tell you anyways. You can remember it because, hey, what's that? Oh, that's an ox. Yeah, the anode is oxidized. It's an ox. Shut up.
Because that's the shape of
And on the side, what's that? Oh, that's a red cat. Oh, because the reduction reaction is the...
Except ours is the red.
See, I
I hate all of you. I don't like any one of you.
Pay the dime to get
Listen, I was here from 7:40 a.m. yesterday to 10:20 p.m. So no, I was not rushing out to Kinko's to get red photocopies made.
Kinko. What the hell is Kinko?
That's why I used to always go in the States. It's a place that does. So the plate that is being reduced, we call that the cathode. The plate that's being oxidized, we call that the anode.
You don't have a red cat.
That's close enough, I think. There we go. Okay, now, drawing galvanic cells can be a time-consuming process. As you can see, like, do you see this picture of it here? Yeah. No, I believe if you'll note. Yeah. Don't tell me I don't cite my sources. Shamelessly.
You like that Durham mosaic.
Listen, here's the deal. I don't think they're great lessons, and they always need to be modified pretty heavily. But in a pinch, they're there and they have nice diagrams. I don't, and I like. Next year will I teach with this note? No, I will make my own. But here's the way a semester goes. I started this semester about 6 weeks ahead, like with 6 weeks worth of stuff ready. And then slowly as you're marking and collecting stuff, that becomes 5 weeks ahead, 4, 3, 2, till before you know it, it's 11:30 p.m. and you're preparing the next day's lesson, which isn't a nice feeling, but that's the reality. That's where you end up. And next year when I teach this, I won't have to do that, and that'll be nice. Yeah, God knows what I'm teaching next year. I'm just going to use this lesson and be like, all right, welcome to grade 9 math. So galvanic cells, let's go, kids. Screw you, I prepared this lesson, I'm using it. Yeah, that's the plan.
We don't
Anyway.
understand this. Too bad. Stop crying.
Okay, so there's a shorthand notation we use, which is simply this. We write always the anode on the left side, and the anode starts with solid zinc.
We teach it equilibrium instead of the quadratic formula. Or as the quadratic formula.
You won't need that shit. We're just gonna replace it.
Okay, so the anode is solid zinc becoming zinc 2+. And you can write the electrons in. You can also not write the electrons in, but we're gonna. And then we're going to draw the salt bridge. All this, that single line is just showing you that that's the reaction that happens. You could just as easily draw an arrow, but this is how they do the shorthand for cells. This double line represents that salt bridge. And we said that was potassium sulfate?
Yep.
Cool.
Potassium? Actually, I don't think it's still sulfate.
Well, sorry, it's solid potassium. Well, no, it would be a salt of some sort, obviously. It's true. That's what I said.
Engineering at its finest.
Now, well, really, that's less effort than an arrow, and it takes up less space. It is more efficient. I'll give them that. What is the cathode in this case? Copper 2 plus becomes, yeah, good. And again, you will definitely see this sometimes written without the electrons. I typically write with the electrons because, sorry?
It is not anode.
Nitrate. They use a nitrate. That makes sense because that's not soluble. Or it's not very soluble. Okay, now, that's the way we do it. So we write the anode on the left, we write the cathode on the right, and we put that double bar to show that we put a salt bridge between the two so that these reactions happen in isolation, so that we can control the happening of the reaction by whether or not we connect them with the electrode, right? In other words, when a battery is sitting in the box, it's not undergoing any chemical reaction. It's not until we connect the positive terminal to the negative terminal that a chemical reaction can occur.
So is it true that if you put the battery in the freezer, it lasts longer?
I don't.
Oh, come on. That was your last.
Here's the deal.
It makes sense.
Does it make perfect sense? Sure. But your number one enemy in science is going, that makes sense. It's probably true. You don't know something until you've done some empirical research to see if it's true. And that's the short version of it. It makes sense, but I have no idea. Now that would be an easy thing to test.
It makes sense just based on the online thing I'm reading. It says that.
I mean, all reactions occur slower at low
It's
temperatures, right?
All this stuff is insulated in water, so the solutions in water.
Yeah, now here's the flip side. I mean, it may make perfect sense, and then you go, oh, wow, when you actually freeze it, freezing causes those solutions to expand slightly, which cracks the barrier between them, and it actually ruins your cell. I don't know. That's the long and the short version. I have no idea. But this is why we do studies in science, not trust. Common sense is your worst enemy as a scientist. And it's so easy a trap to fall into, to go, that makes sense to me, it must be true. The first foundation of science must be, and this has nothing to do with this lesson, but if you learn one thing out of my course, and I think I demonstrate this daily, the first foundation of science is you must be ignorant and aware of your own ignorance. An arrogant person cannot do science. Somebody who thinks he already knows the answer has already given up on the scientific method. You must be willing and prepared to acknowledge that your best understanding of how things work doesn't explain the universe, because for years, our best understanding of how things work led many very brilliant people to be convinced that the Earth was the center of the whole universe and that the celestial things around it revolved around it, embedded in glass spheres. That was our best understanding. And we look back at those people and go, oh, that's so stupid. But it made perfect sense. It did. And they did. And just to be clear, these were not schleps. They did incredibly complex calculations. They knew an incredible amount of information about the world around them, but they were satisfied with their answer. You know, the killer app of humanity is dissatisfaction. I believe that fully, that the thing that makes us work is that we're not satisfied with half-assed answers to things. You know, does anyone know what epidemiology is? Epidemiology is the study of the spread of disease. Epidemiology became a field of study when a French doctor took it upon himself to say, I wonder what the difference, and probably from quite a, because I know a few doctors, and they're not the humblest lot, probably from quite a puffed up position, asked himself, I wonder how much better the health outcomes are for people who can afford to see a doctor versus people who can't. And this is in the 19th century in France, and so he does some study of this. He looks at the health outcomes for his patients versus the population at large, and he discovers that you are twice as likely to die from an communicable illness if you have a doctor's care. because they didn't yet have sterile practice. So they're cutting you open, but they're doing so with dirty equipment because they just didn't know. And this is the foundation of epidemiology, that this help that they thought they'd been providing was harming people. It requires a willingness to embrace your own ignorance. Anyway, that's the end of my spiel about the value of ignorance, but I think it is a wonderful thing.
Ignorance is a bliss. So jokes of you.
All right, now what I want you to do, shh, and this should not, what I want you to do, and this should not take you more than 5 minutes, is example 1 below. I want you to write the half reactions for a battery, or a cell rather, using nickel and copper, and then I want you to write the shorthand notation for it. Should not take you long.
Wasn't it Aristotle that did the thought experiment that said, oh, everything is faster than lighter things?
Yeah, exactly. This became accepted wisdom. You know, like, it is all well and good to reason through things, but you must confirm things empirically. We value Einstein because 50 years after he told us, hey, things that move faster should move through time slower, we were able to put an atomic clock on a plane and have it fly and leave another one on the ground. And lo and behold, the one on the plane flying around moved slower. You know, we venerate him because his thought experiment was later verified by calculus, right? Like, and it's crazy to think, right? But, you know, these amazing people, and again, I'm in an astronomy class right now, so it's where my head is at.
Oh, is that a good one?
I am. It's so good. I'm really, really, really enjoying it. And I'm just taking it online. It'd be way better to be going. And I'm also taking it condensed, right? The 12-week course in 4 weeks,
Yeah.
which is a little intense.
But it's like
But I get excited to go home and study. Like I look forward to it. I get kids in bed, I get the stuff done for your class here, and then like midnight I finally get to put my astronomy lectures on, and I get excited. I'm really enjoying it. And it's not like, it's also got me excited. I now want to take a second year class that has a bit more math in it.
Yeah.
It is not very mathy. There's a bit of math. Like there's definitely some, but it's basic enough. I mean, the math is nothing. And then the nice thing is, I'll tell you right now, if you do take it, just be aware that every semester the tests and exams are essentially identical.
Yeah.
So when he says you can go to the library and look up the past year's tests and exams, I think he even posts them on the website for you guys as well, and we did for us. 80% of the questions are recycled questions. Maybe 20% are new each time around.
What is this?
You know it. I'm waiting for my final examiner, but I got a 98.2 going in.
Did you do the exam already?
Yeah, first half. I'm taking the second half. Like the 2 separate courses.
Oh.
One PO2. So.
Six math?
About 3.5.
No, the first year is not going to be fun.
Did you learn about Weems law?
Yeah, I know.
There you go.
Just
You got black fiber.
That's right. Okay, so what are the 2 half reactions here?
Nickel solid
Solid nickel.
turns into nickel aqueous plus 2 charge,
Yeah, and
2 electrons.
good. Okay, what's the second half reaction? Mashinsky, go.
He doesn't know because he's
Copper with the charge of 2 plus and it's aqueous.
Yep,
Plus 2 electrons
good.
yields solid copper.
Very good. He may have been talking, but he's clever enough to figure it out. What would the shorthand notation be? Yep.
Nickel solid and then a single line. Nickel 2 plus aqueous.
Yep.
Plus 2 electrons.
I'm going to leave the electrons out on this one, just to show you that you can do it either way.
Double line.
Yep.
And then Cu2 plus.
Yep.
Aqueous.
And then you'd put the 2 electrons in, but I'm going to skip them.
Single line and copper solid.
Very good. Very good. Okay. So there we go. Now, again, if I would actually build this, it would mean that I would have to have a container with that salt bridge between the two. And on this side, I'd have a plate. And what would that plate be made of? Yeah, it'd be nickel. And what would be in solution around it? Yeah, nickel something, nickel ions, right? But we could say sulfate. And then on this side, I would have to have a plate that was, and in the solution around it? Good. And what's going to connect them? There we go. And again, remember that those sulfate ions are able to pass through this bridge. There we go.
So, like, the sulfur.
Sulfate, yep.
Go to the other side, but only left half of that one plate just stop. The lower one out on that side.
The sulfate ions have to move to balance the charge.
Right.
They are able to move through, but the other ions are not.
Right, but so if they keep moving through.
They will not run. They will not run out before the plates run out.
Okay.
You make sure you have enough in solution that you're going to run out of other materials before you run out of that. Good question, by the way, but by the nature of it. Now, you've probably been saying to yourself, this is all well and good, Orlando, but where's the math?
Where's the math?
No, thank you.
I missed the math.
Where's the
I
last Orlando?
There you go. Well, guess
I
what?
understand.
Jessica Radko, it's your day.
Oh.
Listen, it's super easy. That didn't prevent me from screwing it up last class, which I'm now going to have to tell them I screwed it up on Monday, but it's super easy.
That's what you said, right?
Do you know that you can make an arc welder out of a 16-volt battery in a microwave?
I've actually heard that. Like you use the magnetron, right?
Yeah.
But anyway, let's focus. So, let's focus. So, standard cells and cell potentials. The point is this. We measure something's electrical ability to do work by measuring its potential. And the unit we use for that is the volt. Yeah, remember that? Grade 9 science? Been a while, right? Or grade 10? No, it's grade 9, isn't it? Long time ago. So we measure potential difference. We measure potential difference in volts. And that is the amount of energy those electrons will have on the anode compared to the amount of energy those electrons will have on the cathode. Now again, if you just let the reaction happen in solution, where would that energy end up? It'd just be wasted. But if we control the flow, and by the way, even in a cell, if I just took a wire and connected anode to cathode, what's going to happen to my battery? It's going to get hot. It's going to get really hot, right? You know this? If you have a short circuit in your home wiring, what's the concern?
Fire.
Yeah, because the wires in the wall will get so hot that they will combust. So if we allow these reactions to happen without an electrical load, it will just produce heat. But if we carry it out in the way we've shown the cell, where we have the wire passing through a load, it will take that differential in energy, and instead of that being released as heat, in which case we would do all of those thermochemical relationships we looked at in Unit 3, we can instead get it to release that energy as electricity, and we measure that in voltage. Does that make sense? So we could do these exact same reactions, and if we just allow them to happen, we could go